Welcome and good late evening. We'll continue today with the question on everyone's mind 15 years ago. The future of intelligent tutoring systems. Will it be model tracing or will it be constraint-based models? The answer, mostly neither, but systems of each type are used at scale. This difference between these two types of systems comes down to how should we assess correctness? And again, the easiest answer is neither. The easiest thing to do is simply design content that has a simple answer and record what that simple answer is. But is this good enough? What about when we want to generate correct answers for a lot of content? What about when we want to assess process as well as final answer? What about when we want to recognize different kinds of errors and why they occurred? And what about when we want to handle answers that aren't just a number or a word? We'll revisit this one next week. So one of the solutions to this is model tracing. And model tracing requires a cognitive model, which in turn requires a cognitive architecture. The basic idea: a cognitive modeling architecture is a framework for developing models of human behavior and learning. And the architecture forces you to make your model plausible based on what we know about human beings. The cognitive framework typically used in this work is ACT-R, or at least an early version of it. And ACT-R stands for sometimes adaptive character of thought, rational, or atomic components of thought, rational, or Anderson's cool theory, rad. Cognitive modeling in education is mostly similar to ACT-R version 2. ACT-R is now on version 7, but the newer versions focus on finer-grained neurological processes, and they're not useful for use in adaptive learning. ACT-R became popular for this because it's got several strengths, particularly accurate and predictive models of human performance at complex tasks, where it models the cognitive processes that lead to various types of behavior, including decision-making, problem-solving, analogy, more with the earlier versions like 2, memory retrieval and strengthening, and learning to be an expert. In ACT-R, the human mind is represented by a set of systems. Each individual system is serial, which means it can only do one thing at a time, but multiple systems can be running at once. And these systems include visual perception, auditory perception, motor skills, productions, which is cognitive skills, and declarative memory, which is facts. Performance is modeled as the interaction between production rules and chunks of declarative memory, and each chunk can have subchunks. And each chunk has a certain strength of activation, which predicts speed and accuracy of recall. And this may be familiar from past weeks. Each production also has a strength of activation. And again, production is a cognitive skill or cognitive behavior. When productions reach a certain strength, they become compiled with neighboring productions into automatized behavior. And this, for example, is how you are able to ride a bicycle without remembering how you ride a bicycle, or how you're able to type on a keyboard without remembering off the top of your head where the F key is. Try to remember that without moving your fingers. Production system models represent performance and therefore skill as a set of if-then rules, again called productions. And they can be written in plain English, although in a cognitive framework like ACT-R, they're written in programming language. And here's an example of plain language productions from Baker et al. For example, if we're trying to find a value on a graph, and we're looking for the value corresponding to a value v, then set a subgoal of looking for v written on the x-axis. If we're looking for v on the x-axis, and value v is written at location x hash on the x-axis, then set a subgoal of looking at location x hash. If we're looking at location x hash on the x-axis, and point F is the topmost drawn in the graphic above location x hash on the x-axis, then set a subgoal of looking across from point P. If we're looking across from P, and y hash is the value on the y-axis horizontally over from P, then return y hash as the value we are looking for. Done. So this set of, 4 productions represents the behavior of trying to find a value on a graph. In model tracing, a production rule model of correct and incorrect behavior, which is referred to as bug rules or buggy rules, is created. And as a student solves problems, the model is used to interpret whether the student's behavior is correct or incorrect. And this information is used to give feedback and for knowledge tracing. The benefits of model tracing: first of all, these productions, because they're general, can be used to answer new problems. So you don't have to type in the answer for every new problem you create. You can create model tracing once and then use it for an infinite number of new problems, including new problems created procedurally. It also provides a natural way for diagnosing problems in the process, for determining where a problem occurs. And it provides a natural link between bugs and the cognition that produces them. But there are several drawbacks to model tracing. For one thing, it's a huge pain to develop. It takes a ton of work. And it's hard to represent the full range of wrong reasoning because there's so many ways that people can get things wrong. It typically represents also only a single chain of reasoning, but a correct answer can often be obtained in multiple ways. And so if a student arrives at the answer in a way that doesn't actually represent the way that the model tracing used, we think they knew one way of doing it, but they might know a different way. So to address these limitations, Alavin and colleagues created example tracing tutors, a method that makes it easier to create a model tracing tutor without actually needing to write program rules and code. Here are some images of CTAT, the Cognitive Tutor Authoring Tools, which realize example tracing. CTAT uses programming by demonstration, where an expert demonstrates the correct behavior on each problem, and then CTAT infers the model tracing production rules to do that. And it can be used relatively easily to demonstrate multiple paths to a solution. It's been used by over 850 authors, which is way more than model tracing tutors, and the systems generated have been used by over 60,000 students, which is way less than model tracing tutors, because Cognitive Tutor Now Mathia was generated by model tracing, and it has over 600,000 students a year. In comparison to model tracing, it's much less flexible. It can represent much less complex types of cognition, but it's much, much faster to develop. The second big paradigm that people were really debating 15 years ago was constraint-based models. Constraint-based models model performance in a very different fashion than model tracing tutors. Instead of trying to represent the processes that lead to the correct answers, they instead represent a list of conditions that must be met for a solution to be correct. If all the conditions are met, the answer is correct. And every one of those constraints has a bug message attached to it. So here's an example of a constraint-based model. Constraint: a base angle of an isosceles triangle is known, and the student has calculated the size of the other base angle. Therefore, the size of that must be this. Another constraint: a base angle of an isosceles triangle is known, and the student has calculated the size of another angle that equals that. Therefore, this other one is a base angle. Or, two angles of a triangle are known, and the student has calculated the size of the third angle, and we can therefore from that calculate the size of that. So constraint-based tutoring has been argued to be more effective than model tracing for ill-defined domains, where student problem solving may take a huge number of paths, but an incorrect solution can be recognized. Now, there's another possibility beyond model tracing and constraint-based tutoring, which is large language models. It's possible that large language models could become the way we do much of this from now on, at least for answers that can be represented verbally, which includes algebra problem solving. This is still at its beginnings, but people are getting really excited about this. Some key takeaways for this lecture: recognizing that an answer is incorrect and recognizing why it's incorrect is a major task for adaptive learning systems. And there are several approaches with different trade-offs, including canned answers that an author creates, model tracing, constraint-based models, example tracing, and large language models, which is a nascent approach. Thank you very much for your time. I'm Ryan Baker. I'll see you next time.